Hello everyone and welcome to Lecture 10. Today we'll explore the basic laws of distribution of discrete random variables, the most important discrete distributions used in probability theory. Here's what we'll cover today. We'll start with why we need standard distributions, then cover 5 key distributions: Bernoulli, binomial, Poisson, geometric, and hypergeometric. We'll compare them and summarize when to use each one. Let me give you a bit more detail about our journey today. We're going to explore the most important discrete probability distributions that form the backbone of statistical analysis. These distributions are like tools in a toolbox. Each one is designed for a specific type of problem, and knowing which one to use is essential for any statistician or data scientist. We'll begin with the Bernoulli distribution, which is the simplest and most fundamental. This distribution describes a single trial with only 2 possible outcomes: success or failure. It's the building block for everything else we'll study today. Next, we'll move to the binomial distribution, which is essentially multiple independent Bernoulli trials. This distribution answers questions like, if I flip a coin 10 times, what's the probability of getting exactly 6 heads? It's one of the most commonly used distributions in practice. Then we'll cover the Poisson distribution, which is used for counting rare events over time or space. This is perfect for situations like counting the number of customers arriving at a store per hour or the number of defects in a large roll of fabric. It's often called the law of rare events. After that, we'll explore the geometric distribution, which answers a different type of question: how many trials do I need to wait until I get my first success? This is useful in quality control, waiting time analysis, and many other areas where we're waiting for a specific event to occur. Finally, we'll cover the hypergeometric distribution, which is used when we're sampling without replacement from a finite population. This is the distribution you use when you're drawing cards from a deck or selecting items from a batch without putting them back. We'll also compare all 5 distributions side by side so you can clearly see when to use each one. By the end of this lecture, you'll have a solid understanding of the most important discrete distributions and be able to choose the right one for any problem you encounter. So let's dive in and start with the question: why do we even need standard distributions in the first place? Why do we need standard distributions? In previous lectures, we built distribution series from scratch for specific problems, but many real-world situations follow the same patterns. Standard distributions give us ready-to-use formulas with known properties like expectation and variance already calculated. They're well-studied and widely applicable across science, engineering, and finance. Today, we'll focus on the most important discrete distributions and when to use them. The Bernoulli distribution is the simplest. A random variable has a Bernoulli distribution if it represents a single trial with only 2 possible outcomes: x equals 1 for success with probability p, and x equals 0 for failure with probability q, where q equals 1 minus p. The binomial distribution represents the number of successes in n independent Bernoulli trials with constant probability p. The possible values range from 0 to n. The distribution formula is P of x equals k equals c sub n. Choose k times p to the k times q to the n minus k. The expectation is n times p and the variance is n times p times q. For the binomial distribution, we need 4 conditions: a fixed number of trials n, 2 outcomes per trial, constant probability p, and independent trials. A classic example is the number of heads in 10 coin tosses. The Poisson distribution counts the number of events occurring in a fixed interval of time or space. The possible values are unbounded: 0, 1, 2, and so on. The formula is P of x equals k equals lambda to the k times e to the negative lambda divided by k factorial. Both the expectation and variance equal lambda, which is the average number of events per interval. The Poisson distribution applies when events occur independently at a constant average rate and 2 events cannot occur at exactly the same time. A classic example is the number of customers arriving at a store in 1 hour. Now let's discuss when to use the Poisson distribution. This is a very important practical question because the Poisson distribution is one of the most widely used distributions in statistics, but it's only appropriate under certain conditions. First, use the Poisson distribution when you're counting events that occur in a fixed interval. This interval could be time, such as an hour, a day, or a year. It could be area, such as square meters of fabric or square kilometers of land. It could be volume, such as liters of liquid or cubic meters of gas. or it could be any other measure where you're counting occurrences within a defined space or time period. The key is that the interval is fixed and known in advance. Second, the Poisson distribution works best when the probability of an event is small. We're talking about rare events here. For example, the probability that a specific customer walks through the door at any given moment is very small. The probability that a specific square centimeter of fabric has a defect is very small. The probability that a specific atom decays in the next second is very small. When events are rare, the Poisson distribution provides an excellent approximation. Third, the number of trials n should be large. This is related to the previous point. When you have a large number of opportunities for an event to occur, but each individual opportunity has a tiny probability of success, the Poisson distribution is the right tool. For example, there are many seconds in an hour, many square centimeters in a square meter, many atoms in a sample. The Poisson distribution handles this situation beautifully. Fourth, the product of n times p should equal lambda, which is a constant. This is the key condition that connects the Poisson distribution to the binomial distribution. Remember from our earlier discussion that the binomial distribution has mean n times p. When n is large and p is small, but n times p equals some constant lambda, the binomial distribution can be approximated by the Poisson distribution with parameter lambda. This is why the Poisson distribution is sometimes called the limiting case of the binomial distribution. Now, why is the Poisson distribution often called the law of rare events? Because it's specifically designed for situations where events are rare, but there are many opportunities for them to occur. In such situations, the Poisson distribution provides a remarkably accurate model. The term law of rare events was coined because the Poisson distribution describes the behavior of rare events so well. Let me give you some examples to make this concrete. Imagine you're counting the number of typos on a page of text. Each character position is a trial, and the probability of a typo at any position is very small. There are many characters on a page, but each has a tiny probability of being wrong. The total number of typos follows a Poisson distribution, or consider counting the number of cars that pass through an intersection in 5 minutes. Each car is a rare event relative to the continuous flow of time, but over a 5-minute interval, you might see several. The Poisson distribution models this perfectly. Or think about counting the number of earthquakes in a region per year. Earthquakes are rare events, but over a large region and a long time period, they occur with some average frequency. The Poisson distribution is the standard model for such phenomena. So the key takeaway is this. Whenever you're counting rare events in a fixed interval, with a large number of opportunities but a small probability for each, and the average rate is constant, the Poisson distribution is your go-to tool. It's elegant, it's simple, and it works remarkably well in practice. Common examples include the number of phone calls per hour, accidents per day at an intersection, defects per square meter of fabric, radioactive decays per second, and emails received per day. All these involve counting rare events over time or space. Now let's turn our attention to the geometric distribution. This is a very different type of distribution from the ones we've studied so far. While the binomial distribution counts the number of successes in a fixed number of trials, the geometric distribution answers a different question. How many trials do we need to wait until we get our first success? Let me give you a concrete example to make this clear. Suppose you're playing a game where you have a 20% chance of winning each time you play. You decide to keep playing until you win for the first time. The number of attempts you need to make, whether it's 1, 2, 3, or even 10 or 20 attempts, that's a geometric random variable. You're counting trials until the first success occurs, not counting successes in a fixed number of trials. The possible values of a geometric random variable are 1, 2, 3, and so on. It's unbounded. In theory, you could wait a very long time for the first success. The probability of waiting a very long time becomes smaller and smaller, but it never quite reaches zero. This is why the distribution is defined for all positive integers. Now let's look at the formula. The probability that the first success occurs on the kth trial is q to the power of k minus 1 times p. Here's why. For the first success to occur on the kth trial, we must have k minus 1 failures first, and then a success on the kth trial. Each failure has probability q, and the success has probability p. Since the trials are independent, we multiply these probabilities together. The q to the k minus 1 part accounts for all the failures before the success, and the p accounts for the final success. Nai. Let's look at the expectation. The expected number of trials needed to get the first success is 1 divided by p. This makes intuitive sense. If the probability of success is high, we expect to wait a short time. If p equals 0.5, we expect to wait 2 trials. If p equals 0.1, we expect to wait 10 trials. The more unlikely the success, the longer we expect to wait. The variance is q divided by p squared. This measures the spread of the distribution. When p is small, the variance is large because there's a lot of uncertainty about when the first success will occur. When p is large, the variance is smaller because the first success is likely to happen quickly. The geometric distribution has an interesting property called the memoryless property. This means that even if you've already had many failures, the probability of success on the next trial is still p. It doesn't depend on how long you've already waited. This is a unique property that only a few distributions have. In practice, the geometric distribution is used in quality control to model the number of items inspected until a defective item is found. It's used in reliability engineering to model the time until a component fails. It's used in sports to model the number of attempts until a player scores. And it's used in many other areas where we're waiting for a specific event to occur for the first time. So to summarize the geometric distribution, it counts trials until the first success. It has values starting from 1. The probability of success on the kth trial is q to the k minus 1 times p. The expected wait time is 1 over p, and the variance is q over p squared. It's the natural choice whenever you're waiting for a first success. That concludes our lecture. Thank you for your attention.